Welcome to this coding problem walkthrough. Today, we'll dive into LeetCode problem number 938, range sum of BST. This problem is a great exercise in leveraging the properties of binary search trees to solve range-based queries efficiently. We'll explore the problem, dissect its constraints, and discuss various approaches to solve it. Let's get started. In this problem, you're working with a binary search tree, or BST, which has a unique structure where for every node, all the values in its left subtree are less than its value, and all the values in the right subtree are greater. Your task is to find the sum of all node values within a given range, specified by the integers low and high. The input will provide the root of the BST as well as these two integers. The result should be a single integer representing the sum of the node values that fall within this inclusive range. This means you need to traverse the tree, identify which nodes meet the criteria, and calculate their sum. Keep in mind that the BST's properties can help optimize this process, as the tree structure inherently divides the values into smaller and larger subsets based on each node. Let's look at an example to clarify. Suppose the BST is represented as an array 10, 5, 15, 3, 7, 0, 18, and the range is defined by low equals 7 and high equals 15. The tree structure would look like this: the root node is 10, with 5 as its left child and 15 as its right child. Then, node 5 has two children, 3 on the left and 7 on the right, while node 15 only has one child, 18, on its right. The goal is to find all nodes whose values fall within the range, 7, 15, and calculate their sum. Using the tree structure, we can identify which nodes to include in the sum by directly comparing each node's value with the range limits. In this first example, the nodes that fall within the range, 7, 15, are 7, 10, and 15. These values are all between 7 and 15, inclusive. Adding these together gives us 7 plus 10 plus 15, which equals 32. As you can see, the structure of the BST helps us quickly identify nodes that meet the criteria without needing to check every single node. This is one of the advantages of working with binary search trees. Now, let's consider another example with a slightly more complex tree structure. For the second example, the BST is represented as 10, 5, 15, 3, 7, 13, 18, 1, 0, 6, and the range is 6, 10. The tree structure shows 10 as the root node, with 5 and 15 as its left and right children, respectively. Node 5 has children 3 and 7, while node 15 has children 13 and 18. Additionally, node 3 has a left child, 1, and node 7 has a left child, 6. Analyzing this tree, the nodes within the range, 6, 10, are 6, 7, and 10. Adding these values together gives us 6 plus 7 plus 10 equals 23. This example demonstrates how the BST structure and the range allow us to focus only on relevant nodes, skipping over others that are clearly outside the range. Finally, let's consider a simpler example where the BST contains just one node. The tree is 1, and the range is 1, 2. Here, the only node in the tree has a value of 1, which falls within the range. Thus, the sum is simply 1. Now, looking at the constraints, the number of nodes in the tree can be as large as 20,000, and node values range from 0 to 100,000. Additionally, the range, low, high, will always be valid, with low less than or equal to high. Key edge cases to consider include a tree with only one node, all node values falling outside the range, and highly unbalanced trees where all nodes are either only on the left or only on the right. These scenarios will test the efficiency and correctness of your solution. To solve the range sum of BST problem, let's first consider a straightforward approach, the brute force method using an integer traversal. The intuition here is based on the property of binary search trees where an integer traversal gives us sorted node values. By traversing the entire tree, we can collect all the node values into a list. Once we have this list, we can filter out the values that fall outside the given range, low, high, and then compute the sum of the remaining values. While this method is simple to implement and ensures we visit every node in the tree, it has some key trade-offs. On the downside, it requires additional memory to store all the node values, even those that may not contribute to the final sum. This makes it inefficient in terms of space, especially when most of the nodes are outside the specified range. The time complexity is O(n), because we visit each node exactly once, and the space complexity is also O(n), due to the need to store the list of node values. Now, let's explore a more efficient approach and optimize depth-first search (DFS) with range-based pruning. This approach takes advantage of the BST property to avoid unnecessary traversals. The key insight is that if a node's value is less than low, all nodes in its left subtree will also be out of range, so we can skip the left subtree entirely. Similarly, if a node's value is greater than high, all nodes in its right subtree will be out of range, allowing us to skip the right subtree. When the node's value lies within the range, low, high, we add it to the sum and continue exploring both subtrees. By pruning irrelevant subtrees as we traverse the tree, we significantly reduce the number of nodes we need to visit. This makes the approach much more efficient, especially for trees where the range covers only a small subset of nodes. The process involves recursively applying these conditions at each node and returning the cumulative sum. The optimized DFS approach offers notable improvements in complexity. The time complexity is O(k), where k is the number of nodes actually visited during the traversal. Thanks to the pruning, k can be much smaller than the total number of nodes n, particularly when the range, low, high, is narrow. The space complexity is O(h), where h is the height of the tree, since the recursion stack only needs to hold nodes along the current traversal path. This approach is efficient, but it does come with a caveat: the conditional logic for pruning requires careful implementation to avoid errors. An alternative to this is the iterative DFS using a stack, which replaces recursion with an explicit stack structure. In this method, we perform the same range-based pruning but iteratively manage the nodes to visit. This avoids the risk of stack overflow in deep or unbalanced trees. For each node popped from the stack, we decide whether to push the left child, the right child, or both based on the node's value relative to the range. The cumulative sum is updated accordingly. The iterative DFS approach has similar complexity to the recursive version. The time complexity remains O(k), where k is the number of nodes visited, and the space complexity is again O(h), where h is the height of the tree. One key advantage of the iterative method is that it eliminates the risk of stack overflow, which can occur with deep recursion on very large or unbalanced trees. However, this approach is slightly more complex to implement compared to the recursive DFS, as it requires explicit management of the stack. While both variations of the optimized DFS are efficient, the iterative method may not be as intuitive to write or understand for all users. This makes it a good choice for scenarios where recursion depth is a concern, but for general use, the recursive DFS with pruning is often preferred for its simplicity and clarity. After evaluating the different approaches, we chose the optimized DFS with range-based pruning as the best strategy for this problem. This method stands out for its efficiency, as it minimizes unnecessary node visits by leveraging the BST property. When the range, low, high, covers only a small subset of the tree, this approach can achieve near constant time performance for unbalanced trees. The recursion-based implementation is also concise and easy to understand, making it particularly suitable for interviews or scenarios where clarity is important. Additionally, it avoids the memory overhead of storing all node values, as seen in the brute force approach, making it more space efficient. While the iterative DFS is a valid alternative, we prioritize the simplicity and readability of the recursive solution. The key insight that drives this optimization is recognizing that entire subtrees can be skipped based on comparisons with low and high. This understanding is crucial for reducing the problem's complexity and achieving optimal performance. Overall, the optimized DFS with pruning offers the best balance of time efficiency, space efficiency, and clarity, making it the ideal choice for solving the range sum of BST problem. To solve the problem of finding the sum of all node values within a specified range in a binary search tree, we first consider a brute force approach using an innerorder traversal. An innerorder traversal is ideal here because it visits nodes in a sorted order due to the BST property, where all nodes in the left subtree are smaller than the current node, and all nodes in the right subtree are larger. The traversal begins at the root and follows the sequence: left subtree, then the current node, and finally the right subtree. As we visit each node, we collect its value into a list or array, which will be used later for filtering. Once we have the list of all node values from the innerorder traversal, the next step is to filter out the values that fall within the specified range, low, high. For instance, if the range is 10, 20, we keep only the values that are greater than or equal to 10 and less than or equal to 20. After filtering, we compute the sum of these values to get the final result. The time complexity of this approach involves O(n) for the traversal and another O(n) for filtering and summing, leading to an overall complexity of O(n). However, it also requires additional space of O(n) to store all node values, which is not efficient when dealing with large trees. This brute force approach, while straightforward, highlights some important insights. The BST property plays a crucial role in simplifying range queries. Specifically, nodes in the left subtree are always smaller than the current node, and nodes in the right subtree are always larger. This property allows us to optimize our algorithm by skipping irrelevant subtrees. Additionally, an inner traversal is a natural fit for BSTs because it produces a sorted sequence of values, making it easy to identify nodes within a given range. However, the brute force method is inefficient in terms of memory usage since it processes all nodes, even those outside the range, which leads us to consider a more optimized solution. Before diving into the optimized approach, it's important to understand the data structures involved. The binary search tree itself is the input data structure, and its properties enable efficient range checking. The second data structure used in the brute force approach is an array or list, which temporarily holds all node values during the traversal. These values are then filtered and summed to produce the result. The reliance on this additional space is one of the key drawbacks of the brute force method. To address the inefficiencies of the brute force method, we can use an optimized approach involving a recursive depth-first search, or DFS, with pruning. This method eliminates the need to store all node values by directly computing the sum as we traverse the tree. Starting at the root, we check whether the node's value lies within the range, low, high. If it does, we add it to the sum. If the value is less than low, we know that all nodes in the left subtree are also less than low, so we skip the left subtree entirely and traverse only the right subtree. Similarly, if the value is greater than high, we skip the right subtree and traverse only the left subtree. This pruning process ensures that we avoid unnecessary computation. After determining whether to include a node's value and deciding which subtrees to explore, the algorithm proceeds with recursive calls on the left and right children as appropriate. The recursion naturally handles the traversal and range checks, and it stops when a null node is encountered, which serves as the base case. At each step, the sum of valid node values from the current node and its subtrees is returned. By leveraging the BST property to skip irrelevant subtrees, we significantly reduce the number of nodes that need to be processed. In the best case, for a balanced BST where pruning is highly effective, the time complexity is O log n. In the worst case, such as when the tree is unbalanced or all nodes fall within the range, the complexity remains O(n). The space complexity of the optimized approach is determined by the recursion stack, which depends on the height of the tree. For a balanced tree, the height is O log n, leading to efficient space usage. However, for a skewed tree, the height can be O(n), which increases the space complexity. This method follows a clear visual flow. Starting at the root, each node is checked to see if its value lies within low, high. If it does, the value is added to the sum. If it's less than low, the left subtree is skipped, and if it's greater than high, the right subtree is skipped. The process continues recursively for valid subtrees, and the traversal stops upon reaching a null node. This approach ensures that only the necessary parts of the tree are explored, resulting in an efficient solution for the range sum problem. Here, we start by defining the basic structure of a binary tree node with the treenode class. Each node has a value, and pointers to its left and right child nodes, which default to none if not provided. Next, we define the solution class, where the main function, range Sum BST, is implemented. This function takes three parameters, the root of the binary search tree, and two integers, low and high, that define the range of values to be summed. Inside the function, we initialize a class-level variable called range_sum to 0, which will keep track of the total sum of values within the specified range. To traverse the tree, we define a helper function called DFS, short for depth-first search. The DFS function takes a node as its input. If the node is none, meaning we've reached the end of a branch, the function simply returns. If the node's value falls within the given range, we add it to the range_sum variable. We then decide which subtrees to explore next. If the current node's value is greater than the low boundary, we call DFS on the left child, as nodes to the left in a binary search tree are smaller. Similarly, if the current node's value is less than the high boundary, we explore the right subtree by calling DFS on the right child. Once the DFS function is fully defined, we initiate the depth-first search traversal by calling DFS on the root node of the binary search tree. This starts the recursive exploration of the tree, ensuring that all nodes within the specified range of low to high are visited and their values are added to the range_sum variable. Finally, after the entire tree has been traversed, we return the value of range_sum, which contains the total sum of all the node values within the range. This approach efficiently leverages the properties of a binary search tree to minimize unnecessary exploration, focusing only on the relevant parts of the tree based on the given range. Here, we begin by defining the structure of the binary tree using a treenode class. Each node in the tree contains an integer value, val, as well as references to its left and right child nodes. We provide two constructors, one that initializes a node with just a value and another that initializes it with a value and its left and right children. Next, we define the main solution class, which contains the range Sum BST method. This method takes three parameters, the root of the binary search tree, and two integers low and high representing the range. Inside this method, we declare an integer array, range_sum, to store the cumulative sum as we traverse the tree. We use an array here to allow updates to the sum across recursive calls. Finally, we use a helper function, DFS, to perform a depth-first traversal of the tree. After the traversal completes, we return the accumulated sum stored in range_sum, 0. The DFS method is a private helper function that recursively traverses the tree. It begins by checking if the current node is null, and if so, it simply returns because there's nothing to process. If the node's value falls within the specified range, between low and high, we add this value to range_sum, 0. This ensures that we include only the nodes that satisfy the range condition. Next, if the current node's value is greater than low, we know that there might be valid nodes in the left subtree, so we recursively call DFS on the left child. Similarly, if the current node's value is less than high, we explore the right subtree by calling DFS on the right child. This logic ensures that we traverse only the necessary parts of the tree, optimizing our search for nodes within the range. Here, we are given a basic binary search tree and a range, 7, 15. Our goal is to calculate the sum of all node values within this range. We start at the root of the tree, which is the node with value 10, and initialize our range_sum to 0. Since 10 falls within the range, 7, 15, we add 10 to our range_sum. This gives us an updated range_sum of 10. Next, we notice that 10 is greater than the lower bound of our range, which is 7, so we decide to traverse its left subtree to check for any additional nodes within the range. As we move to the left child of 10, we encounter the node with value 5. Since 5 is less than the lower bound of our range, 7, it is outside the range, so we skip adding it to our sum. However, larger values might still be in range, so we explore the right subtree of node 5, where we find the node with value 7. The value 7 lies within our range, so we add it to the range_sum, which now becomes 17. After this, since 7 is less than the upper bound of our range, 15, we check its right subtree, but it is null, so we backtrack to the root node, 10, and proceed to explore its right subtree. Here, we visit the node with value 15, which is also within the range. Adding 15 to our sum gives us a new total of 32. From node 15, we attempt to traverse both its left and right subtrees. Its left subtree is null, and its right subtree leads to the node with value 18. Since 18 exceeds the upper bound of our range, we skip it and conclude this traversal. After traversing the entire tree, we find that our final range_sum is 32. Moving to the next example, we are given a new binary search tree and a range, 20, 30. Here, the range is such that no nodes in the tree fall within it. We start at the root, which is the node with value 10, and initialize our range_sum to 0. Since 10 is less than the lower bound of our range, 20, it is outside the range, so we skip adding it and move to its right subtree, where we might find larger values that fall within the range. In the right subtree, we visit the node with value 15. Similar to the root, 15 is also less than the lower bound of our range, 20, so it is outside the range as well. Consequently, we skip adding it to our sum. We then attempt to traverse the right subtree of node 15, but it is null, so the traversal ends here. Since we did not encounter any nodes within the range, the final range sum remains 0. In the next example, we are given a binary search tree and a range, 1, 15, which covers all nodes in the tree. We start at the root, which is the node with value 8, and initialize our range sum to 0. The root node, 8, lies within the range, 1, 15, so we add it to our range sum, which now becomes 8. We then traverse both its left and right subtrees. In the left subtree, we visit the node with value 3, which is also within the range. Adding 3 to our sum gives us a total of 11. From node 3, we explore its left child, the node with value 1. Since 1 is within the range, we add it to our sum, resulting in a new total of 12. Both the left and right children of node 1 are null, so we backtrack to node 3 and proceed to its right child, the node with value 6. The value 6 is within the range, so we add it to our sum, making the total 18. Both children of node 6 are null, so we return to the root node, 8, and move to its right subtree. In the right subtree of the root, we visit the node with value 10. Since 10 is within range, we add it to our range sum, which now becomes 28. We then move to its right child, the node with value 14, which is also within the range. Adding 14 to our sum gives us a final total of 42. The left and right children of node 14 are null, so the traversal ends here. After exploring all nodes in the tree, the final range sum is 42, which is the sum of all node values within the range, 1, 15. The time complexity of the range sum BST function depends heavily on both the structure of the binary search tree and the range defined by low and high. In the best case scenario, if the range is very small, the algorithm can skip over most of the tree, visiting only a small subset of nodes. For a balanced BST, this means the time complexity is O log n, because the traversal is limited to just a few branches of the tree. On the other hand, in the worst case, where the range includes most or all of the values in the tree, the function will have no choice but to visit every single node. Here, the time complexity becomes O n. On average, if the range covers a moderate portion of the tree, the complexity generally scales with the number of nodes visited. For balanced trees, this is often expressed as O k, where k represents the number of nodes within the range, low, high. Now, let's think about the space complexity of this algorithm. The memory usage is primarily influenced by the recursion stack created during the depth-first search traversal. In the best case, where the traversal is minimal, the height of the recursion stack is directly proportional to the height of the tree. For a balanced BST, this means the space complexity is O log n. However, in the worst case, such as when the tree is skewed into a single branch, the recursion stack will grow to the full depth of the tree, leading to a space complexity of O n. Importantly, the algorithm does not require any additional space for storing data structures, as the sum is calculated incrementally using a single variable. Overall, the space usage is directly tied to the depth of the tree and the nature of its structure. To compare, a naive approach to solving this problem would involve traversing the entire tree and checking each node's value against the range, low, high. This method has a time complexity of O n in all cases, as every node must be visited regardless of the range constraints. The space complexity would also be O n in the worst case, due to the recursion stack of a skewed tree. In contrast, the optimized DFS approach used here takes advantage of the BST property to skip unnecessary branches. For instance, if a node's value is less than low, the left subtree is ignored, and if a node's value is greater than high, the right subtree is skipped. This significantly reduces the number of nodes visited, especially when the range is small relative to the tree size. In terms of time complexity, this optimized approach achieves O k in many cases, where k is the number of nodes within the range. The space complexity remains tied to the tree's height, which is O log n for balanced trees and O n for skewed ones. This efficiency comes from ensuring that each node is visited at most once, with the recursion stack depth bounded by the tree height. When solving this problem, there are a few common mistakes that can trip up candidates. One is assuming that the input is always valid. For instance, you might encounter an empty tree or a tree with just a single node. Failing to account for these edge cases can lead to null pointer exceptions or undefined behavior in some languages. This is a key area interviewers look at to test your thoroughness. Another frequent pitfall is ignoring the unique properties of a binary search tree. Some candidates treat it as a generic binary tree, which can result in unnecessary traversals or incorrect results. Remember, the BST property that the left subtree contains values less than the root, and the right subtree contains values greater allows us to optimize our solution significantly. Additionally, inefficient range checks are another issue. Visiting nodes that clearly fall outside the range, low, high, adds unnecessary computations, which can slow down your solution, especially for larger trees. Finally, overcomplicating the recursion is something to avoid. Complex and convoluted recursive logic can make your code harder to debug and follow, which is a major drawback during interviews. Strive for clarity and simplicity in your recursive solutions. Another mistake to watch out for is neglecting iterative solutions. While recursion is a popular approach, it's important to consider iterative methods as well, particularly in environments with limited stack space. Being able to implement both recursive and iterative solutions showcases your versatility as a problem solver. Now, when optimizing for this problem, always keep the BST properties in mind. For example, if a node's value is less than the low value, you can skip its entire left subtree, as all values there will also be less than low. This type of pruning is a critical optimization for both time and efficiency. You should also weigh the trade-offs between space and time when deciding on an approach. Recursive solutions are often simpler but require h space for the call stack, where h is the tree's height. On the other hand, iterative solutions can be more space efficient, using additional space, but they often require more verbose code. Additionally, testing for edge cases is essential. These might include an empty tree, scenarios where all nodes fall within the range, cases where no nodes are in the range, or trees that consist only of left or right children. Lastly, remember to communicate clearly during interviews. Make sure to explain how you're leveraging the BST properties to optimize your solution, as this demonstrates a strong understanding of the problem and your approach to solving it. This problem shares concepts with several related problems, and exploring them can deepen your understanding of how to work with binary search trees. For example, LeetCode problem 700, Search in a Binary Search Tree, focuses on traversing the tree to locate a specific value. Problem 530, Minimum Absolute Difference in BST, involves finding the smallest difference between any two values in the tree. Another related problem is 501, Find Mode in Binary Search Tree, which asks you to identify the most frequently occurring values in the tree. These problems often require similar traversal techniques and make use of the BST properties, so studying them can be very helpful. Now, when considering alternative approaches to the range sum of BST problem, one option is the brute force method using inner-order traversal. This approach involves traversing the entire tree, collecting all the node values, filtering those within the range, low, high, and then summing them. It's straightforward and simple to implement, but it's not the most space efficient, as you'll need extra space to store the list of node values. The time complexity is O(n) for the traversal, plus O(k) for filtering the values, where k is the number of nodes within the range. Another approach you can use is an optimized depth-first search, or DFS, implemented recursively. With this method, you traverse the tree while skipping unnecessary subtrees that fall outside the range, low, high. For example, if a node's value is less than low, you avoid traversing its left subtree entirely. This approach leverages the BST properties effectively, making it both time-efficient and elegant. The time complexity is O(n) in the worst case, where the tree is unbalanced, but for balanced BSTs, it's O log n. The space complexity is O(h), where h is the height of the tree, due to the recursive call stack. Alternatively, you can implement an iterative inner-order traversal using a stack. Instead of recursion, this method explicitly manages the traversal stack, allowing you to process nodes iteratively while skipping those that fall outside the range. This approach shares the same time complexity as the recursive DFS O(n) in the worst case and a space complexity of O(h) for the stack. While it avoids recursion and is useful in environments with limited stack space, it can result in more verbose code. Understanding and being able to implement both recursive and iterative approaches shows that you're well prepared to tackle this problem in a variety of contexts. Great job making it through this problem. To recap, we used the unique properties of binary search trees to calculate the range sum efficiently. We discussed both brute force and optimized approaches while analyzing their complexities. Remember, practicing with tree-based problems is key to mastering them. Thanks for tuning in. Don't forget to like, share, and subscribe for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!